Hi class, it's Mrs. Kane, and I'm here with your next e-learning video. This should be Friday's lesson, and today we're going to be talking about something called the continuously compounded interest formula. Okay, so to talk about this formula, we're going to start by taking a look at the compound interest formula that we talked about on Wednesday. Okay, so if we take a look at this formula, A equals P times 1 plus R over N to the NT power. Okay, so remember, P is the initial amount of the investment, R is the rate, N is the number of times interest is compounded per year, and T is time. Okay, and what we're going to talk about today is what happens as N gets really, really big. Okay, so the more often that interest is compounded, okay, what happens to that base of the exponent or the multiplier? Okay, so if you look at the table that we are given here, we're specifically going to zero in on this base of the exponent. Okay, so this is the number that is being multiplied repeatedly. Okay, so we're going to look at what happens to that base as the number of times interest is compounded gets bigger and bigger. Okay, so N again is going to start, we're going to look at N equals 10. So if interest is compounded 10 times per year, okay, that base is 2.5937. If it's compounded 100 times, it goes up to 2.7048. If interest is compounded 1,000 times, notice that multiplier only goes up a little bit. And then 10,000 times, again, 2.718. Notice how close these numbers all are. Okay, and then if interest is compounded 10,000 times per year or even 1,000,000 times per year, now you'll see that that multiplier, if we round to the nearest thousandth, it doesn't budge. Okay, so we call this a limit. As N gets larger and larger, that multiplier approaches the number 2.718. Okay, and this number is going to become very important as you move through your math classes in the future. So this number, 2.718, has a special name. It's kind of like the number pi. Okay, so we call this number E. Okay, E is an irrational number. Okay, so that means it's not a repeating decimal. Okay, it's not something that can be written as in fraction form. Very similar to kind of pi. We think of it as 3.14, but 3.14 pi actually keeps going. Okay, so we think of E as 2.718. Okay, and there is an E button on your calculator. Okay, so if you hit the second button and then the division sign, and you hit enter, you will get more digits of E. Now it continues to go. Your calculator can only list so many numbers because it runs out of room. Okay, so we're just going to think of it as 2.718. We're going to have the nearest thousandth when we talk about the number E. Now, the reason we're talking about this number E is because it's important for the next type of interest. Okay, the last type of interest we're going to talk about is called continuously compounded interest. So if interest is compounded continuously, I want you to think of that as the number of times per year approaches infinity. So we can't even imagine. It's just a continuous amount in which the interest is compounded. Okay, so we saw the relationship between that as N gets bigger and that base becomes E. So what you'll notice in this next formula called the continuously compounded interest formula is that it involves a base of E. Okay, so we already know the compound interest formula. Okay, that involves an N for the number of times interest is compounded. So you'll notice for the next formula, the continuously compounded interest formula, okay, we use the equation A equals P times E to the RT. Okay, and that RT is in an exponent. It's a product in the exponent. So this is also known as the PERT formula. Okay, and you'll notice we no longer have N because N is not defined by a number. It's compounded continuously. Okay, also note that E is a number. We're going to use the button on our calculator. We're not going to use 2.718, and it's not a variable. So when we plug numbers in, we're not plugging anything in for E, okay? We're going to use the button on the calculator. All right, so let's take a look at a couple problems. In 2018, $1,000 is invested, and it earns 5% interest compounded continuously. So there's your keyword. That's how you know you're using the PERT formula. How much will the investment be worth in 4 years? All right, so we know that P is 1,000. Okay, E is not a variable, that's a number. We're going to use our calculator for that. R is 5%, so we're going to write that as 0.05. And then T is 4 for 4 years. So all we have to do is put that together using the equation. 1,000 times e to the 0.05 times 4. That's the exponent. If you have an older model of a calculator, you got to type that with parentheses. If you've got a calculator like the one on my screen, you do not need the parentheses. So we've got 1,000. Now if you hit second ln, on the left side of your calculator, it's 2 keys above the on button. If you hit second ln, it will put E on your screen and it will automatically raise that to a power. Okay, so I'm going to type in 0.05 times 4. I'm going to hit enter. And my investment is now worth $1,221.40. Okay, and because we're dealing with money, I'm going to round to 2 decimals, 40 cents. Okay, a little variation. During which year will the investment be worth $1,500? Okay, so the variables stay the same. So all of these are the same. Oop, I'm sorry, they don't all stay the same. We're trying to figure out these two are the same. The original investment is $1,000. The rate is still 0.05, but now we're trying to figure out how long it takes for the investment to be worth $1,500. Okay, so that's called the mature amount. Okay, so we want to know how long it takes for A, the new amount, to be $1,500. Okay, so notice we're going to put $1,500 in for A. We're still going to put 1,000 in for P. And we're still going to put 0.05 in for R, but this time we're trying to find how many years. So my exponent is T. Okay, and notice I needed a number for A because we can only have one variable in the problem if we're going to solve it. All right, so we're going to try to solve this equation for T. We don't really have any methods yet to solve for an exponent, but I'm going to show you a new one. So we're going to start by getting that base of E by itself. So I'm going to divide both sides by 1,000. And I get 1.5 equals e to the 0.05t power. Okay, and from here, I'm going to be creative with the calculator. I'm going to let y1 equal 1.5, and I'm going to let y2 equal e to the 0.05t. Okay, so in the calculator, I'm going to type 1.5 in for y1, and then I'm going to hit second ln, and I'm going to do e to the 0.05. I'm going to use x instead of t. Okay, because that's the variable my calculator uses. And then I'm going to hit graph. Okay, and what you're going to notice is you're going to have a horizontal line at 1.5, and then you're going to have your exponential curve. Okay, and this is going to represent e to the 0.05t. And this intersection point right here, the x value of the intersection, is going to answer your question. All right, so I'm actually going to change my window. I'm going to make my max 15 so we can, actually I'm going to change it to 20 because that doesn't really look like a very exponential curve. So I think if we kind of kick that window out, we'll see the exponential part of that curve a little bit better. Okay, so you can see it pull apart a little bit better. So what we're going to try to do here is we're going to find the intersection of the curve and the line. So when you do intersection, you just hit second trace and select number 5 for intersection. And then you just kind of get close to the intersection and you can hit enter 3 times. Okay, and so notice that the intersection happens when x equals 8.11. Okay, so instead of x, I wrote t equals because we replaced x with t. Okay, so it takes 8.11 years for that $1,000 to reach an amount of $1,500. If we read the question carefully, it says, during which year will the investment be worth $1,500? Okay, so the investment was from 2018, so we're going to add 8 to 2018, and the investment is going to reach that amount sometime in the year 2026. Okay, so hopefully that made sense. We will learn about another way to solve exponential equations after spring break when we start talking about logs. All right, let's go ahead and try another one. It says, Mr. Teacher invested $3,300 in an account that earns 4.7% interest for 10 years. How much will the investment be worth if interest is compounded continuously? Okay, and then we're also going to figure out how much it will be worth if it's compounded quarterly. So if you think you understand this, go ahead and pause the video, okay, and try these two problems. Okay, but otherwise just stick with me. I know you might need at least a couple more examples. So when it says compounded continuously, we're going to use what we call the PERT formula. And then when it says it's compounded quarterly, we're going to go back and use the compound interest formula. Okay. All right, so the initial amount in the investment is $3,300. The rate is 4.7%, so I'm going to write 0.047. And the t value for both of these is 10. Okay, so if it's compounded continuously, I'm going to do 3,300. And then I'm going to do E, and then my exponent is going to be 0.047 times 10. Okay, so 3,300. I'm going to hit second ln, and then I'm going to do 0.047 times 10. Okay, so the amount is going to be $5,279.98. Okay, so we round to the nearest hundredth when we're talking about money, unless it specifies otherwise. Okay, and then same information for the next one, okay, but we're using a different equation. So P is 3,300, 1 plus, okay, in this problem we have to add in an n value. If it's compounded quarterly, n is 4. So we're going to do r divided by n, so 0.047 divided by 4. And then the exponent is n times t. So n is 4 times t is 10. So the exponent is 40. So in the calculator, 3,300 times 1 plus 0.047 divided by 4. And then I'm going to raise that to the 40th power. You could also just type 4 times 10. Okay, and so when it's compounded quarterly, the investment is worth $5,265.53. Okay, so notice that you make a little bit more money if it's compounded continuously versus quarterly. Okay, and that's because interest is added more often. All right, I'm going to end today's lesson with just a little bit of graphing practice. We're going to look at a couple problems where the base of the function that we're going to graph is e. Okay, and since e represents approximately 2.718, okay, if e is the base of your function, then it's always going to be exponential growth, okay, because 2.718, that base is greater than 1. All right, so we're going to use our calculator to go ahead and graph these functions and find the important features. Okay, so the first one, I'm going to hit second ln, and I'm just going to type in e to the x. And then if you hit zoom 6, we should all see the same graph. I actually have to go back and fix mine. Okay, so the first thing I want you to look for is the horizontal asymptote, okay? And as long as you don't have any numbers that you're adding or subtracting after your exponent, you can think of that as plus 0. So the horizontal asymptote is going to be y equals 0 unless there's a vertical shift up or down. Okay, so I'm going to go ahead and write that in, y equals 0. Okay, so x-intercept. Okay, let's go ahead and sketch this first. I'm going to go to table. I need to change my table set real quick. Okay, so I'm going to hit second graph. I'm going to look at the table. I'm going to pick a couple of points. Now, they're not going to be all nice points. I see I have a point at 0, 1. And then I see, let's say, -1, and let's just say 0.4. And then on the right side, I see 2 and 7.4. Okay, so just like 3 points where you can kind of get a sense of what's going on in the graph. So we have a point at 0, 1, And then negative 1.4, that just means that it's getting really close to that x-axis on the left side. And then the 2, 7.4 kind of models that growth. Okay, so I'm going to use a nice smooth curve. I'm going to approach the x-axis, and I'm going to sketch a graph. Okay? Now, if I ask you for the x-intercept and there's a horizontal asymptote at y equals 0, that horizontal asymptote is a line that's approached, but the graph never touches it. So we're going to say none. Now, this does not mean you always write none. Okay, it's if you look at the graph and you have an asymptote at 0. Okay, so some of you are just writing none for all the x-intercept questions. When we look at number 4, that might make a little bit more sense. Okay, your y-intercept is 0, 1. Domain is negative infinity to positive infinity. The range, okay, the lowest y value is just above 0, and then it's going to keep going up. So the range and the horizontal asymptote go hand in hand. We want to use a parenthesis there instead of a bracket because the graph does not touch y equals 0. All right, so the last problem, we're going to do a couple transformations here. We're going to add 1 to the exponent, and we're going to subtract 4 after the exponent. Okay, and what you're going to notice, this graph moves left 1. That's not super obvious by looking at it, but it should be obvious that it gets moved down 4 because that horizontal asymptote goes down 4 with the graph. So you'll see that it flatlines not at 0, but at y equals negative 4. Okay, so that horizontal asymptote, y equals negative 4. Okay, so again, I'm going to go ahead and look at the table. I'm going to try and get some points that I can put on the graph. I see there's one at negative 1, negative 3, and then 1, 3.4. That should fit on the graph. And then I'm going to go up and I'm going to grab, what else can we put on here? Let's do negative... let's do negative 6, and we'll just round to negative 4. Okay, so negative 6. Oh, we can't. It's getting closer and closer to negative 4, so sorry. That's not a good point. Let's go the other way. There we go. Okay, so we can fit, we need one more point that can fit on the graph. Let's just do negative 3 and negative 3.9. Okay, so negative 3 already gets really close to 4 right there. Negative 1, negative 3, and then, 0, negative 1.2. We should have used that one because we have to find that anyway. So your y-intercept is 0, negative 1.28. It says to round to the nearest hundredth if necessary. Okay, so I should have put that on there. 0, negative 1.28, and then I had 1 and 3.4, so I'll stick that on there. Okay, so these points are enough to make a nice smooth curve. We get the general shape. Okay, so the table also has the y-intercept 0, negative 1.28. Now, this one does have an x-intercept. It's right here. So to find the x-intercept, you're going to find the 0. So go to your graph, hit second, calculate, and select number 2. Okay, you're going to pick a point on the left of the 0 and hit enter. Pick a point on the right of the 0 and hit enter. Pick a point in between, and so your x-intercept is 0.39, 0. Okay, domain negative infinity to positive infinity. Your range is negative 4 is the lowest value. It's not included, it's just above that, and then it's going to keep going to infinity. Okay, so hopefully these graphing examples help kind of clarify some of the questions you might have had earlier in the week. Thanks for watching. Please complete the short assignment that's in the daily assignment folder. I will be giving you points for completing that.